Okay, this video is a classic proof using contradiction to prove that the square root of 2 is irrational. Now, first of all, this is really only something for your information. Many of you may be math majors, or I should say some of you may be math majors and may see this again. It's a nice example of a way to use contradiction proofs, but there's no expectation that you would ever have to do anything like this semester, and certainly no expectation that you would have thought to do this on your own. But it's a nice little proof. It's sort of a classic standard example of contradiction, and one that you would certainly see again if you took a general proof course. Now remember that proving by contradiction means you assume the opposite, and then before we can go about a proof of by contradiction here, we have to make sure we understand what rational and irrational are. So we may have not used these numbers in a while, but rational numbers, if you look at the first 5 letters here, ratio, rational numbers are basically integer fractions in lowest terms where p and q are integers, and q cannot be 0. Okay. Now, if you think about a number like 5, 5 is rational, right, because it can be written as 5 over 1. Certainly a half is rational. Okay. You have decimals like 0.73, which is written as 73 over 100. Right? These are also rational numbers. But there are some famous irrational numbers. The square root of 2 is one of them. Pi and e are some of the other irrational numbers. Okay. So if we're going to prove that the square root of 2 is irrational, right, by contradiction, we're going to assume that the square root of 2 is rational. Okay? And then we're going to show that this is not possible, that somehow there's a contradiction in what we know about square root of 2 and rational numbers in order for this to hold. Okay. So if the square root of 2 is rational, we'll start our proof that the square root of 2 must be p over q for some p and q. Right? And again, the assumption here is that the p over q is in lowest terms, p and q are integers, and q is not equal to 0. So I'm not going to rewrite that over here because it's sitting over here. The key is actually going to be in lowest terms. Okay? If we're going to do any kind of algebra or anything like this, we don't really want this square root of 2 in here, so we're going to square both sides. And when you square both sides, right, you're going to get 2 equals p squared over q squared. And if you multiply both sides by q squared and just return this around, you'll get p squared equals 2q squared. Now since p and q are both integers, p squared is really 2 times an integer, right, L, which means p squared is even. Okay? Now, this is something established in the book, that if p squared is even, that implies that p is even. Now that, on its own, would be its own separate proof. We can call that sort of a lemma that we would go off to the side and prove. But this is established, and we're just going to ask you to take our word for it at this point. You can certainly explore some perfect squares like 16, right? It's 4 squared, and 25 is 5 squared, and so on. Any time the perfect square is even, the number you're squaring has to be even, but that can be proven. So we're just going to, right now, assume that p is even. Okay? Well, if p is even, then p must be some 2k. All right? Okay, now let's go back to this line over here. Right? This line over here says that p squared equals 2q squared. Well, then 2k quantity squared must equal 2q squared. 4k squared, just squaring the 2k expression, equals 2q squared. Divide by 2 on both sides to solve for q. And we'll see something a little bit interesting here, that q squared is 2k squared, which means it's really 2 times some other integer m, which therefore means that q squared is even. And we've already established that means that q is even. Okay? So why did we do all this? Well, we now have a situation here where p is even and q is even. Right? However, this square root of 2 is supposed to be a rational number. It's supposed to be p over q. And in particular, p over q is supposed to be in lowest terms. Well, if p is even and q is even, then if you divided p over q, right, if p and q are both even, right, then P over Q is not in lowest terms, right, because you could divide top and bottom by 2, and that is, in fact, the contradiction. Okay? So if we assume square root of 2 is irrational, then we have to do a little bit of creative work to come up with the contradiction. That's always sort of the challenge in these more open-ended contradiction proofs, is you have to find a contradiction. And in this case, it was the fact that P and Q are in lowest terms. The ones that you'll see in the book will be more like the other example, where you're going to have at least a certain amount of one type, and those are really the only ones you'll need to worry about this semester. This is just for information. You can erase this from your memory banks if you find this confusing, but again, those of you that are math majors might see this again in a proof course.